Okay. Good morning, everyone, for this distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Sanjay K Madria, Curators Distinguished Professor, Department of Computer Science at Missouri University of Science and Technology. The title for today's talk is Efficient Revocation in Attribute-Based Encryption Scheme for Secure Data Sharing in Cloud. Dr. Madria is a distinguished professor in the Department of Computer Science at the University of Missouri-Rolla. He has published over 300 plus journal and conference papers in the areas of cybersecurity, mobile and sensor computing, big data and cloud computing, and data analytics. He won 5 IEEE Best Paper Awards in conferences such as IEEE MDM, IEEE SRDS. He is a co-author of a book published with his 2 PhD graduates on Secure Sensor Cloud, published by Morgan and Claypool in December 2018. He has graduated 20 PhDs, 33 master's students, and currently have 12 PhD students. And he has received funding from various federal agencies, including NSF, NIST, ARL, ARO, AFRL, DOE, Boeing, CDC, ORNL, Honeywell, over $18 million. He has been awarded Japanese Society for Promotion of Science Invitational Visiting Scientist Fellowship and American Society for Engineering Education Fellowship. In 2012 and 2019, he was awarded NRC Fellowship by National Academies. He's an ACM Distinguished Scientist and served as an ACM and IEEE Distinguished Speaker. He's also an IEEE Senior Member as well as IEEE Golden Core Awardee. Dr. Madria, it is a great honor to have you as part of the webinar series at the University of North Dakota. Thank you so much for spending your time this morning with us, and it's a pleasure to have you here, and the floor is yours.
Thank you. Good morning, everyone, and thanks for inviting me. Can I share my slides now?
Yes.
Okay. So my talk today is based on the work which I have done with my PhD student. And as you can see, the title is Collision-Resistant Revocable Attribute-Based Encryption Scheme for Secure Data Sharing in Cloud. So first thing is, of course, the motivation and why we share the data in the cloud, why security is very important, what others have done in this domain, and what we have proposed. And I'm going to talk about the technical scheme and algorithm details, experiments, evaluation. And this is, as I said, like we have multiple papers in this domain. And what I'm going to talk today is only part of the work, but the rest you can see as we have a couple of journal papers and one conference paper based on this work. So the first thing is, why we share the data, right? So that we can scale. And also there are many other advantages, like users can access easily from the cloud. It's always available because your service provider will guarantee, right, that it's 99.99% available. You can always scale. It does not matter how many users are there. And of course, you don't have to worry about failures, right? That server has failed because your service provider will take care of those issues. And of course, low maintenance because you're not maintaining any server and so on. So there are several benefits of sharing data through the cloud. So the question now comes that why we need security. Of course, very first thing is that data can be very sensitive and you do not want others to read, and especially those who are not authorized to read. Also, the cloud can be malicious, can collude, for example, with a malicious user or a user who's been revoked from the system. And also, it's possible that your service provider has poor security measures and practices. And of course, as we know, there are several stories of attacks on cloud servers. So the idea is, can we encrypt the data and then store the data in an encrypted form in the cloud? So as you can see that owner, and owner could be an individual user or individual owner or a company, and they basically can encrypt the data and store in the cloud, and then authorize different users by giving them the keys so that they can go to the cloud and access the data they are authorized to. Several schemes, for example, in this domain are there, and RSA, for example, you can encrypt. There is identity-based encryption where basically you're encrypting the data and then you are giving keys to the users based on their identity. Of course, as you can see that this breached the privacy because then we know who are the users. Broadcast encryption is where you have subscribers, for example, and then you are sending these keys to those subscribers. Again, as you can see, the subscriber can change and so on. So then you have high overhead. So the next one comes, which is very popular, is the attribute-based encryption, because here you are not doing per user, for example, you're encrypting based on attributes. Let me give an example here. So as you can see that the access control structure can be defined using attributes, and you can provide very fine-grained access control. If you see in this screen here, that you may have an encrypted data, you may have, for example, the public key you can encrypt, and then you have a access control tree here. So if you have a user like Alice, and if Alice secret key basically is based on the attribute emergency and fire, then Alice, as you can see here, and emergency and or fire, the Alice can access. And if you have a Charlie whose secret key is based on non-emergency and medical, as you can see, non-emergency is not there. So Charlie cannot basically access the information. So as you can see that here, it's a one-to-many encryption. A single copy of the ciphertext has been generated because it is not based on per user. So it will provide, for example, user-centric privacy because users are not directly involved. Now, of course, that looks good, but then there are several challenges when we use the attribute-based encryption. There are several types of attacks which are possible, and I'm trying to talk in this particular today's talk is two types of attacks, type 1 and type 2. So what is a type 1 attack? For example, you have multiple users there, and they may have access control to some attributes, but they can cooperate with each other and share their attribute-based keys so that they can satisfy the policy. And type 2 attack is actually more dangerous in the sense that here a user has been revoked who cannot actually decrypt a file, even if they have enough attributes to satisfy the policy, but the revoked user can cooperate with a non-revoked user and try to decrypt. So let me show you an example here. So if you see, I have 4 users, Alice, and as you can see that Alice has attributes in secret key, research, and PhD, and revocation status is a non-revoked, right? So it's a valid user. Bob is another user who basically has attributes research and MS, but as you can see here, it's a revoked user. And then Eve, who basically has attributes research and undergrad in the secret key, and also it's non-revoked. And Charlie has non-research and MS, and it's also non-revoked. So on the right-hand side, you can see the access policy. Now, what basically can happen in case of type 1, where 2 users who are non-revoked users basically can combine their attribute keys. So for example, Eve and Charlie, if they combine, they can basically see research and MS, right? Because as you can see in the access control policy, research and MS is possible. And then the type 2 is where Bob, who's a revoked user, and try to collude with either Eve, for example, or Charlie. So if they, let's say Bob join hands with Charlie, then research and MS again, and they can see, though they are not authorized. For example, Charlie is not authorized to see research. So these are these two types of attacks which are possible. And I'm going to basically discuss solutions for type 1 and type 2 attack. So of course, I'm not working in vacuum, right? There are others who have tried to address these two types of attacks, as you can see in the related work section here. But the solutions which they have provided have some drawbacks or deficiencies. So as you can see that the very first one, the HER, multiple papers, and they basically do not provide solution for type 2 attacks. Crypt cloud is prone to type 2 collision attack, and also they require secret key redistribution by semi-trusted entity. And in our solution, we avoid this. Again, flexible and SRABE, they have very inefficient revocation because non-revoke users need to update the secret keys. So our goal here is to provide an efficient revocation. So basically, non-revoke user secret keys should be unaffected, right? Because otherwise, it's very inefficient solution that you are revoking some users, but you may have hundreds of users, and then you have to, for example, redistribute the keys to them. It should be resilient against both type 1 and type 2 collision attacks. And also, we can basically provide secure revocation. That basically means that the scheme we have designed does not require any semi-trusted entity to achieve any revocation, like attribute manager and so on, which has been assumed in some other works. So let me talk technical from this point onwards, and I'll make sure that you'll get this also. So some notations, as you can see here, I'm using some symbols, ZP, which is basically a integer modulo prime P. And then I have two elliptic curve groups of order P, G, and GT. And I have a hash function which can take a sequence of 0, 1s and map it to the group G elements. So basically, we have a bilinear map. And the main important property is the bilinearity. So as you can see that there is a generator for the group, small g. And the main property is that E of G to the power A and G to the power B is same as E of G to the power AB. And also if it has non-degeneracy property. And the most important is that it's computable. So you can basically do these group operations efficiently. So how we are doing this? So let me give an example for secret sharing. So as you can see on the left-hand side, I have an access policy. Let's assume that I have a Boolean formula here, right? A and B, or B and C, and A or D, and so on. So assume that A and B are basically attributes. So any satisfying subsets for this Boolean formula will be like AB, for example, or BCD. The idea is basically that we will distribute these keys into these attributes like A, B, and B, C, D. So on the right-hand side, you can see a tree. And basically, I'm going to show you a numbering scheme here. So what we do is we have a global counter as 1, we have a vector as 1. And when the Boolean operation is and if the left hand is or, as you can see. So what we do if it's and, we distribute 1, 1 to the left-hand side. And to the right-hand side, we distribute 0 and -1. And our global counter is 1. Then since this is now OR gate, so what we do, we have the same 1, 1 on the left and the same 1, 1 on the right. If you see here again, this is an OR gate, so it will be same 0, -1 and 0, -1. And then we basically increase the global counter to 2. Now, as you can see here, I have 1, 1. So same thing, I'm going to do 1, 1, 1. For the right hand, I have 0, 0, -1. Now, after this, I basically change the global counter to 3. And now 1, 1, as you can see, this is and. So I have 1, 1 and 0, 1. Of course, as you can see that the global counter is 3. So I have to basically add 0. And then same thing here, that it is the right-hand side. So I have 0, 0, -1. Since A and D have no other further child nodes, they will be the same. Now what I do is I'll basically will take this and transfer this into this access policy matrix M. I basically have done nothing. I have just captured this 1, 1, 1. As you can see in the first row, 1, 1, 1, and my attribute is A here. And of course, I'm trying to pad 0 so that the length of all these rows remains the same. So I have 0, 0, minus 1. As you can see, padded with 0. The attribute is B. And now I have 1, 1, 0, 1, as you can see here. So I have the attribute V and so on. So I have just basically taken all these vectors and represented in this matrix. And I have row, which basically a column vector, which basically has the attributes. The most important thing, as you can notice here, is any satisfying set of attributes will always have this vector as 1, 0, 0. So if you see, for example, M0, which is A, B, and then M4 is C. So ABC, basically, if you add these vectors like M0 and M1, right, you have 1, 1, this will become 0. And then if you add M4, which is 1, 0, 3, and 4, right? So you basically get 1, and the rest will be the 0. That basically means for any satisfying attributes, you will get as the vector as 1, 0, 0. So now I have this linear secret sharing scheme where my access policy is the matrix M with L number of rows and N columns. And row I basically maps the row I of this matrix to the attribute. So the row i's of M to the ith attribute of the policy. Then I have a column vector here, V, which basically has the secret, which to be shared, and that belongs to the integer modulo P. And R2 to Rn are basically random numbers. So I generate a lambda I, which is my vector V with my matrix Mi, that will give me the ith valid share of S. So what basic idea is that I have this weights, which belongs to the integer modulo P. So if I have Wi lambda I, then basically I can get S, right? So the idea is that to recover S, I need the Wi and lambda I. So the next is I'm going to talk about how the scheme works. So here is an example to show the scheme the algorithm basically. So I have here 8 users, as you can see, U1, U2, U3, U4, U5, U6, U7, and U8. And my revoke list of user is U6 and U8. So you see the capital U is all the users, and my revoke list has U6. As you can see, U6 is here, and then U8. So what these red nodes basically shows is these are the nodes which are in the path of these revoke users. Okay? So I use a subset cover problem here. So I'm going to find the subset cover for the nodes which have not been revoked. So as you can see here that my revoked list is U6, U8, and non-revoked list is RL prime, which basically has U1, U2, U3, U4, U5, 7. So if you see that the Y2 basically covers U1, U2, U3, U4. U5 is covered by Y12. U6, of course, is revoked. U7 is covered by Y14, and U8 is revoked. So if you see my cover, subset cover problem basically has Y2, Y12, Y14, and these 3 nodes basically cover all the non-revoked users here in RL prime. So the next is how basically we generate different algorithms. So the algorithm for the public key, master key, ciphertext, secret key, and your basically the message. So first thing is a setup, which have the number of maximum attributes, maximum rows, and so on. Then we have to generate ciphertext. Of course, we have to encrypt. So encryption involves the public key, the matrix M. You saw the row column. The M is the message, and RL is the revoke list. The SK is the secret key. So that algorithm is keygen, which has the primary key, which has the master key, which has the number of attributes you have, capital S, and the number of users. And then, of course, for decryption, we have PK, we have SK, and the ciphertext. So once we decrypt, you basically get your message M. So let me talk about these different algorithms next. So as you can see here, the first is the setup. And in the setup, I have the public key. So as you can see here, the example of the tree, which is my top. Then I have, of course, group G, GT. I have E of G, G alpha, G to the power A, G to the power, which are the generators, and my hash function. My master key basically has G to the power alpha and beta. So here, basic idea is that I can choose the GYI for this tree tau such that I have this GYI belongs to the group for each node yi of tau. As you can see, the yi nodes are all the nodes in this tree. And of course, U1 to U8, as I said, they are the users. So how we encrypt? So first thing is, as you can see that for all the nodes yj, as you can see, all the yjs are here, which belongs to the cover for the non-revoke users, right? So who are the nodes? Y2, Y12, Y14, right? These are basically the YJs. So for that, we have CYJ, which is denoted as, which is basically nothing but G to the power S, YJ. And here I'm showing you, for example, that CY2, as you can see for non-revoke user, is GY2 to the power S. CY12 is G to the power S, Y12. CY14, G to the power S, Y14. Right? So this is how you basically going to encrypt. So this is my CYJs for the example. Then the next thing I have is CI, which is G to the power A lambda I. Remember that lambda I is part of that secret. Then I have the hash function rho I minus R. Then I have another component C prime, which has the G, and S is the secret, beta, capital D is nothing but G to the power R. So if you see here, my ciphertext basically has this M is the message. So basic idea is that, of course, I'm encrypting. When I decrypt, this part should be taken out, and then we can, of course, get my message. So, of course, again, to remind that the ciphertext components to revoke in this case is the U6 and U8. Okay. So this is my encryption. The next is, of course, keygen. So we are going to generate the secret key for the attributes of, let's say, the user UK, and S is the set of attributes. So now, as you can see, for all the YJs, which belongs to the path of the users. So as you can see, when I'm saying path is like for U1, Y8, Y4, Y2, and Y1. These are the nodes in the path of the user U1. Then for that, we generate KYJ, and which is nothing but G to the power alpha plus AT, GYJ to the power 1 by beta. For all X belongs to S, so remember that S is a set of attributes. So for all the attributes, we generate KX, which is the hash to the power T. And then we have L, which is G to the power T. So now, as you can see that for the user U1, I'm just showing you the example that here we'll generate for each user this. So for KY1, as you can see, generate G alpha AT G of Y1, okay? And then for KY2, it generates G of Y2, KY4, it generates G of Y4, and then KY8, it generates alpha plus AT, GY of 8. So this is the membership key component of user U1. I'm just showing you for one user, right? So same thing for U2 and U3 and U4, you will basically have these components, okay? So basically you're generating the keys for those users. The next is how you decrypt. So if you recall, we have the ciphertext for my message M, and then we have this, the access control matrix and the attributes. So if you recall, we have for all YJ belongs to the cover, we have CYJs, and then we have the, for all alpha, for all I, we have the CJs, C prime and C. Now I have the attribute secret key for user UK, which I just showed you in the previous slide. So what I'm going to do here on the left-hand side, I will show you how we decrypt. So for the decryption, I'm going to basically generate two components, capital P. So what I'm generating here is E of KYJ C prime. So now if you see here, I have the C prime G to the power S beta. So I'm replacing C prime by G to the power beta S. And then the second thing I have is here KYJ. So if you see in the attribute secret key, I have KYJ. So I have basically replaced with that. So if I do a very simple, calculations, I get P as this. Then I'm going to generate another component, capital Q, which is E of CYJ G. Now, if you see here, my CYJ is given here, right? So I'm just replacing CYJ with this and and then the power S. Okay. So you see here GYJ is power S. So GYJ, and I'm taking that power here by the property, right, of the bilinearity. So now let me show you the full calculations here. So I have P, which basically is calculated based on this. I have generated this. I have Q. So what I'm going to do next is generate a component W, and W is nothing but this P divided by this. So if you see, I have Q here, and then the product of E of Ci of L, E of D KQI weight Wi. So if you see that, I'm going to basically replace everything from here, right? So once I replace all these components, basically I get the product of E, GG, AT, WI, lambda. You see that this is the important component, right? Because this summation of this is nothing but your secret. So if I basically again simplify, as you can see that I have AT out because the product, I get a sigma of WI lambda I. And now I replace Q by this entity here. So once I do this, I basically get this. So if you recall, my ciphertext was M into this, right? So what I'm going to do, I'll take C and divide by the W. C is my ciphertext, as you can see here. And then the component which I have generated here, which is my W. And then I basically divide, I can get my M. So basically I get my message. So now let's talk about how this scheme can handle first type 1 attack. Okay. So now let's take that same example, which I gave earlier. So here now I'm replacing U1 as Alice, U6 is Bob, U2 is Eve, and U3 is my Charlie. And attributes in secret key is, let's say, research and PhD, as in the example, research MS. And see here, it's a non-revoke. If you remember, Bob is a revoke, right? And U6 I also consider, right, a revoke user. So U6 is a revoke user. Eve U2 is a non-revoke with research and undergrad attributes. And of course, it's a non-revoke. Charlie is U3. Of course, no, U3 is non-revoke, right? So from this, only U6, if you remember, is the revoke. And of course, I'm just taking one example. So non-research and MS. So now in the secret key of Charlie, and since U3 is a non-revoke user, of course, it can generate KY1, KY2, KY5Y, because if you see the path of U3, right, you have Y110, Y5, Y2, Y1, right? So it generates KY1, KY2, KY5, KY10. And then if you see the H component before, so I had H here. So you see that KX is nothing but HX, right? The hash to the power T. And remember that X is my attribute, right? So if you see here, I basically have H, and this is my attribute, non-research here. And also Charlie has another attribute, which is MS, right? MS. And the T, if you remember, right? So this is T3 corresponding to the user U3. And I have L, which is another component, G to the power T3. Similarly, now for SK, which is secret key of E for U2, and U2 is here. So you see Y9, Y4, Y2, and Y1. So I have KY1, Y2, Y4, and KY9. And similarly, I have the hash of research T2 and undergrad T2 and L of G2, right? And this is your basically the access control policy. So now what happened is that E basically cannot decrypt by colluding with Charlie. So the idea is that what if they collude, right? So if they collude, they basically have to see that these t's, right, which are different. So the exponent T2 in Eve's SK and T3 in Charlie's, they are different. And in order to combine this, you basically cannot combine because this is like solving the logarithmic problem. So in order to get this, you cannot combine this to satisfy the access control policies. So if I do the example now, let's for type 2 attack. So for type 2 attack, if you remember, I'm going to join hands with the non-revoke user and a revoke user. So let's say here now the secret key for Bob U6. So here is the U6 revoke user, KY1, KY3, KY6, KY13, which is in the path. And then I have the hash of research D6 for U6, MS D6. So same thing as I just mentioned, SK for Eve is KY1, KY2, Y4, Y9. In this case, remember that U2 is a non-revoke user, right? So this is the path. So now what happens if I see my ciphertext for the revoke list? So if I generate CY2, as you can see, my CY2 is for the node Y2 here, right? So GY2, C12, I have this CY14. So this is, if you remember, this is for the non-revoke user. Then I can generate C1, A lambda I, H for research. Again, this is just considering that research is that attribute. And this is, again, just to remind you, is coming from here, right? Here, right? So I'm generating those ciphertexts. So I have here C1, I have here C2, which is research, MS, and PhD, because they have joined hands, right? And then I get my C prime, I get my D. So this is my ciphertext, which is my M into GT alpha S, right? Now, if I want to again solve this problem, that Eve, of course, remember that this is a valid person, right? The U2. So this Eve has, okay. Now, but the problem is that this will not work with Bob's this, because again, you see here, I have a T2 and T6, which are different. And in order to successfully decrypt, basically the Bob, who's a revoke user, has to solve the discrete lock problem. So this is how you basically block the type 1 and type 2 attacks. So let me talk about the architecture, and then I'll show you performance evaluation and some other related stuff which we have done. So as you can see here in this architecture, that I have the attribute secret keys. Here are the data owners, of course. They'll encrypt the data stored in the cloud. And then the cloud service provider, of course, there are some public parameters. If you saw in the scheme, right, I have alpha, betas, and so on. They are stored there. And then the data users basically will go to the cloud and get those public parameters and try to decrypt. So here is the performance evaluation. So the first thing is, of course, the key generation time, key gen. And I'm comparing it with this other schemes. So this is our scheme, and these are some other schemes. As you can see here, the attributes in secret key is 5, 10, 15, 20, 25. And here is the time in milliseconds. So basic idea. So this is like the base scheme. So we have to be close to this. So as you can see that here is our scheme, which is close. And this is using the linear curve of 152-bit. And this is using the nonlinear curve of 159-bit. So here again, you can see that our time for even nonlinear curve, right, is very close to the baseline. And these are, for example, for other algorithms like Crypt Cloud is, you see here is like about 650 seconds, and we are like about 20 seconds. Same thing here, you can see that for Crypt Cloud, sorry, so user call is here. And of course, there are others who still are much far in terms of the key gen, right, generating the keys. So this is the encryption time. So as you can see here is our scheme. And as you can see, of course, we are taking a little bit more encryption time, except for user cloud. So here, the idea is that how many nodes you have in the structure. And then this is the linear curve, and this is the linear curve. Of course, again, like our time is more if you see in the encryption. Now, here is the decryption time. So again, the number of attributes. So you see that we are very close, to the baseline. As you can see, all others, they take more time for decrypting. Same thing here for the nonlinear curve. As you can see, we are very close to the baseline. Now, this is the most important result, I would say, where, as you can see that irrespective of how many users I have 0 key update time. As you can see in all algorithms, they will update some part of the key, but we don't have any key update for any of those type 1 or type 2 attacks. So as you can see that this is the most important, I would say, the result compared to others, that we don't generate any updates. Now, here is the conclusion and future work. So as you can see that the idea is that we have proposed this scheme which can handle the type 1 and type 2 attack. And we basically try to provide a collision attack safe scheme. And we do user level revocation. Future work can work on the attribute-based revocation. So remember, I'm talking about user-based, right? U1, U2, U3. But you basically can revoke the attributes as well. Now, we have done that actually in those journal papers. And also, you can have the dynamic access policy in a mobile environment. And I'll show you this, that we also implemented this in a mobile environment. And then idea is, can you create these schemes which are quantum safe? So let me see how we can adopt this scheme in a combat cloud environment in a battlefield. So here in a battlefield, as we know, that there are multiple groups working on many different missions. So the access control policy will be based on many different groups. So we can make some changes in the algorithm. So of course, for setup, the attribute authority need to form the overlay tree during the setup, because somebody has to know who are the groups, right, who are working on in the battlefield. And the during key generation, all nodes in the path of the overlay tree should be covered. So for example, all these things have to be covered because they are part of that group. For encryption, if sharing involves other group members, then subset cover algorithm should include the corresponding nodes, for example, in the other groups. For decryption, of course, we don't have to make any changes. So the benefits of having the overlay tree is that members of the same group are in a close proximity of each other. So that will generate a smaller ciphertext, and that will have a faster encryption. So that's why we are doing this like a group wise. So they're like the group basically may be working in a smaller region, for example. For end-to-end communication, of course, encryption and decryption is possible without the intervention of any information server. We need to put less trust on the information server since it's storing the encrypted ciphertext. Group isolation. So if a group is operating in isolation, then the members only need to have knowledge about its own subtree. Multi-group operation, that means if you are having multiple groups, then you have to have the knowledge of all the subtrees which are there. And that information reveals no additional information other than that there are members associated with other groups. So here is the Combat Cloud architecture. So as you can see that we have multiple members in a group. Then this is like another group with some other mission. For example, this is the attribute authority, and they will generate these keys and give it to Humvees, for example. And these nodes basically will interact with the Humvees. So Humvees here is like acting like a cloud. So as you can see that PKs are shared, and then you have the secret keys which are coming from attribute authority to the groups, and same thing here. And then the ciphertext information is generated and sent it to the Humvees. So that's the end of my talk. Maybe I finished a bit early. Maybe we have more time for questions.
Thank you, Doc.
And show
ahead.
you some implementation. of this. So we have implemented this whole scheme in a mobile environment. And let's see if I can find my. I didn't plan for it that I'll have time to show that, so I'm just trying to find if I can. I'm just trying to see if I can find that handy, the implementation. Yeah, can I share now? Yeah.
You should be able to.
Yeah, so I'm just sharing my paper. So we actually implemented this whole thing. I don't know if you're able to see this. Can you see that?
We can see it.
Okay. So we basically implemented the architecture I just showed you. And this is actually a demo paper. So if you see, of course, it's quite complex in the implementation because, we have to implement all our algorithms, right, at the bootstrap. If you see here, let me make it a little even bigger. So you see here that we have mission start, setup, secret keys, primary keys, and then we have this attribute authority who will distribute, for example, the keys. So here is the data sharing. We have implemented, if you see here on the phone, using the Google Nearby. So we search the nearby device, it can create connection, and it can share some metadata information. You see that send the encrypted photos and AES key to the chosen user when they are available, for example. Of course, you see here, I'm generating the AES keys, encrypting. We call this scheme Revocation ABE for that mobile environment. And then, of course, we are doing some machine learning stuff as well there to find which user should get what and so on. So we have implemented this, and you can see some screenshot here that I have home, users, manage user, add user, mission. And once you see that bar chart, if I scan, I basically get my attribute access policy on my phone. So as you can see here, that's the current users in the mission, Alice, Bob, Colin. You have delete users. So these are functions like you can delete users, add users. You can add new mission. And the main thing is like, the policy will be created. And if you see here, of course, backend implementation has been done. It was quite complex actually to implement the backend, where you basically have all these access trees and access control policies. And next, of course, is how to connect. And you see here the policy and receiver selection, member revocation you can do. So this is very interesting. So you can see the policy on your phone, and then you can, in dynamic way, you can revoke a user so that your data will be actually encrypted on your phone with a new access control policy. I don't know if I have that here to show you, but you see that it has the attributes, what attributes that person can see. And then again, some other attributes. We are in this application, actually, we were sharing the photos and sharing the photos with the people who are authorized to see those photos, for example. So of course, it has some how to generate the photos and all, but the main important thing was here that how you can basically revoke. I actually have this app on my phone as well. So what I'm basically saying that we actually changed this algorithm so that it can be adopted for a mobile environment. And this was very interesting because we could do this dynamically, as, for example, the battlefield progresses, you want some of the users to be revoked, not revoked because they're malicious, but in this case, it's like, let's say the mission has changed. So if their mission has changed, you basically want to re-encrypt the data with a new access control policy, which you can do on your phone. So when you basically disseminate, these users will get it, but they'll not be able to decrypt. So I think this is the paper which appeared in MDM under the demo. I'll stop here, I think, if you have questions.
Thank you, Dr. Madria. Great presentation. Now I'd like to encourage everyone to post their questions in the Q&A. See, we already have a few. Dave asks, does this method become susceptible to compromise if the Boolean satisfiability problem becomes easier to solve?
So it's basically boils down to, if you see that example I showed, is that it has those hashes, right? And if you cannot recover, of course, you can, as I said, like it's a logarithmic discrete problem. If you can solve that, yes, you can break that, but not with the Boolean satisfiability problem.
Okay, thank you. Dr. Oku asks, thanks so much for your great presentation. I would like to ask, what do you think about the potential integration of your scheme with blockchain or Tangle? Have we studied?
Yeah, we have not done that, but definitely you can have this, for example, policies can be stored in the blockchain, and the blockchain probably can solve this problem that you may have a dynamic policy. Right now, for example, as I said, in the booster phase, for example, I will get all the users and I have to know, for example, the revoke user. But if your new users have been added, my algorithm, for example, will not work, right? Because I already have that access control tree. So maybe then the blockchain, you can do these things dynamically and users can connect and get the new policy, which is not possible, like, for example, in the battlefield environment, maybe, but yeah.
Okay. And then Mira asks, do you have any other scenarios where we can use this scheme?
Definitely, for example, in a disaster management scenario, right? Not everybody should be able to see everything. And also it's not about seeing that, they should focus on what their mission is. So we can basically have this based on the attribute-based access control policy.
Okay.
Like, because in a disaster, so many different agencies are involved and they all have different mission.
Thank you. Narup asks, could you comment on whether you've considered cryptanalysis?
Yes, it is there in the paper, definitely, that we have done the security analysis.
Okay. And I had a question. You briefly mentioned making this secure against quantum computers. Could you just give an overview of what kind of direction that would take?
This is like how you make it more complex so the quantum computers cannot decrypt. I've not done anything, but that's the basic idea,
Okay.
Can it quantum safe,
Thank you for your presentation.
Because, these discrete lock problems and all probably, can be solved on those computers.
Mhm. Okay. Well, you'll be receiving a plaque and a certificate of appreciation for contributing to our webinar series. It was a pleasure hearing your talk. I'm sure we'll be in touch.
Thank you.
Thank you.
Thanks a lot. Bye-bye.
Bye.
Thanks everyone for attending,